Last time around, we were talking about managing sort of sleep for entire systems and kind of issues that one ends up facing in there. And kind of the bottom line was that the whole idea of making the whole system go down, go to sleep and back up. It's basically the one complication is that we want to maintain some semblance of a service. If that wasn't there, then the problem was relatively straightforward. So a lot of contortions were basically coming from that we want to maintain that presence, and at the same time, we have all these constraints. That is, we cannot go around changing protocols arbitrarily. We need to make sure that that transition, like when we give control over, when we let a proxy represent a sleeping machine, that handover from machine to proxy and back kind of happens cleanly. So, and the other thing is it's sort of almost impossible to maintain full functionality. So part of the design space is that what functionality do you seek to maintain? Should connections which are already there, should they remain undisrupted? Do you allow new connections? All those kind of questions sort of that come up. So I described kind of the schemes, kind of Apple's kind of scheme, work out of Microsoft, which was this one where one issue that we also learned, I also mentioned is the issue that management is a thing. So you cannot, a solution which does not require essentially whatever dollars you are saving on the energy side, if they disappear on additional system administration, then that's a sign of complexity. So those were kind of the issues that we were facing. And the Microsoft solution basically is to have the sleep proxy. And before that, I described the solution where on every network card, in a sense, you have a little processor. And that's not too far off, like if you were to do it now, to have the big dot little type architecture. So you have a tiny processor which stays up, you still have network connectivity, and then when you need the big resources, you kind of bring things back up. So this is compared to sort of things which not too long ago, when machines went to sleep, there was basically no way to maintain any network presence. Okay, so that was one. Then the next stuff, these are slides I had already kind of gone over, so I'm going to skip over them. There have been other attempts. So there was another follow-on work out of UC San Diego, and the concept there was the following. So these are all variants on kind of the similar kind of ideas. So what they do is that they have a server where for every machine in the enterprise, in their case it was the CSE department. So for every machine in the CSE department, there is also a virtual machine which is running on the server, but that virtual machine is dormant but is identically configured. So it's essentially with minimal effort, it is able to kind of take over. So for each host that you need to proxy, there's a VM image, and it is identically configured network-wise. And then what happens is that every desktop, every machine which can potentially go to sleep, it basically has an agent which talks to this proxy server, and then when it decides to go to sleep, it kind of arranges for things to be handed over. And again, similar kind of issues where you have to make sure that the IP address gets transitioned, that any future packets are going to head to the virtual image. All of those things need to be taken care of. So similar sort of idea. They kind of also posted numbers on kind of savings and all that they got. Again, this is kind of in their department-wide kind of things, and they were running it on a whole bunch of computers. So significant savings sort of to be obtained. Perhaps the most widely deployed was Apple's Wake on Demand, which they introduced, as I mentioned, as part of this ZeroConf standard and this Bonzor service. I think until recently, so the PC side of the world has been way too fragmented. So something like this took sort of time to emerge, and I think now it is there. So this bullet is not strictly true. On the Apple side of the world, because they had control over both sides, the network infrastructure and the devices to some extent. So such a solution came earlier on. So what Apple does is that it integrates the proxy into their airport Wi-Fi access points, which are I don't know if any of you have those, but these are essentially access points plus router, bridges, and simple firewalls. They can also do some storage and stuff like that. Main idea is the following, that there is a service, the proxy service, which runs on the base station. And then they have this the zero con for Bonzor system. So the zero con for Bonzor is designed for not just power management, it's actually a richer service. So the way it works is the following, that if as the word zero cons implies zero configuration. So Apple's goal was to make small scale networking, like a local area network, small enterprise network, to be very painless. So that you do not have to go around assigning anything. You should be able to discover stuff like, for example, if I want to find out is there a music library on the network, I shouldn't have to configure an IP address and whatnot. I should just discover it. So what ZeroConf does is, ZeroConf has this notion of that machines using something called multicast DNS. So using that and kind of using basically multicast routing, they arrange to advertise their services. So the idea is that you can advertise a service on a local network, and then any other machine which is interested in your service can discover it. This basic concept has been sort of tried in many different sort of standards and companies and all over the years. Like many years ago, Sony was pushing for something called HAVI, which was home audio video interfacing, and Sun Microsystems had something called Ginny. These were all kind of takes at making what is called a service discovery easy. So you advertise a service that I'm a printer, I can print PDF files, or I'm a music player, I can play music with these capabilities. So you somehow find a way to advertise it, and then anyone interested in your service can basically publish a query saying, I'm looking for a printer which can do PDF, and then network protocol will arrange for information about that to be sent back. So those of you who have Macs, if you go onto your Safari browser, you can enable this thing called Bonzor, and then if you press on it, you would see all the web services, all machines which are running a web server which are advertising that. Okay, so you do not have to know that, oh, there is a machine here or like a sensor there which is which is running a web server. They actively advertise it by registering it onto this. So it's not as if there is necessarily a single server where registration is happening. It's kind of a distributed service. So this notion of services is there. So you advertise services. When someone is looking for a service, they're going to put a request. You or someone who has knowledge of that service are going to respond saying, okay, I can accept this service, and then the transaction takes place. So the proxy server is built upon that concept. So the idea is there's a machine, and it offers certain services, but it needs to go to sleep. So what it will do is it will transfer the responsibility for responding to requests for these services, as in, is there a service responding to that or doing some minimal transaction? It hands that over to the base station. So essentially, the base station runs the proxy server. If my laptop is offering, let's say, SSH service or printer service and whatnot, then when my laptop goes to sleep, it transfers information necessary for the base station to respond on this laptop's behalf onto that to that airport. While this machine is sleeping, let's say some machine now makes a request saying, is there a machine offering a PDF printer service? And let's say my machine did, but my machine is sleeping. Then the base station is going to respond on its behalf, and then meanwhile, kind of next time around when my machine wakes up briefly to check for any request, the access point will tell it, now there is a request for you, and it will continue from that. So any service that is registered with Bonzor, regardless of what the underlying protocol is, it gets automatically handled by this. Okay. So wake on demand is kind of the second piece behind this. So ZeroConf is giving you the service model. The wake on demand is a separate piece, which basically ties in with this ability of the newer Wi-Fi cards to go to sleep, wake up, maintain their registration, go back to sleep. So again, kind of, you would see that your laptop periodically wakes up. If you have a hard drive, it will make some noise and all. Checks with the base station, renews its registration, goes back to sleep. So that's what happens in this part. When a request is made to access a shared item like this, then basically the initial transaction, that is, there exists such a service and all, is handled by the proxy. But then whenever the sleeping machine wakes up, then it is informed that it needs to take over. And then after that, it goes back to sleep. So these two pieces come together, the zero conf and kind of the ability to do wake on demand over a wireless link. And that's kind of Apple's solution. Now, again, if we look relative to the other things, it maintains network presence, but of a limited form. So it's not as if the actual music or files or a printer is connected to the access point. Okay, the actual machine has to wake up. So if a Skype call comes in, let's say for example, then the only thing that the access point knows about is that yes, there is a service here that this laptop has, but it will arrange for the laptop to be woken up. Unlike the UC San Diego solution with stubs, where there could be actual application code running on the proxy and do a little bit of application level handshaking, there is no such concept out here. So that's the wake on demand. It's like I said, it's probably the one which is commercially most available currently. Another nice solution, which again came out of Microsoft and University of Michigan, is a solution called LiteGreen. And here they again make use of virtualization, but unlike the UC San Diego solution where there's a real machine, there's a virtual machine. When the real machine is going to sleep, its state gets moved to the virtual machine. Here what they do is they actually, everything is a virtual machine. So even when I'm working on my real machine, I'm not working on OS running on my real machine. I'm actually interacting with a virtual machine running on my real machine, and I'm interacting with that. So at all times, you are working with a virtual machine. And then when it comes time to sleep, all you do is you migrate the virtual machine. Okay, so that's kind of the difference out here. There's always a virtual machine. There's always virtualization, except what is happening is the server when you're going to sleep, you basically kind of move the virtual machine over. What problem do you see with that, if any, or like advantages, disadvantages? Relative to, let's say, the solution where the virtual machine was always running here. I did not have virtualization here. I just moved the state here. Thoughts? Yes. Huh?
So I have a question. So for the machine on this site,
Mm-hmm.
does that require a full-blown computer to be running in order to access the server?
Yeah, I mean, yes. So the way virtualization works, you would have an OS running out here. Usually, there are certain Linux releases which are optimized for that. So these are stripped down version of Linux is capable of running. They run something called hypervisor, through which they host virtual machines. Okay. So you have the native operating system, and then on top of it, you're running a virtual machine. So kind of just go back in the animation. So I have always have virtualization. So if I'm running Windows, that Windows is running in the virtual machine, then running on top of my Linux running some sort of a hypervisor. Okay, so that's the basic structure. You could also always kind of run multiple machines if you want also, but what they are advocating is that instead of having any native installation, we'll always run inside the virtual machine so that we can then just move the virtual machine over. So I guess question I was asking was the following. I mean, essentially, moving the machine over is a clean way of moving all the relevant state, right? Your network addresses, your application state, everything is kind of just moving over. So you do not have to deal with kind of the messiness of transferring. So like So there's certainly attractive positives. But the question is kind of what negatives do you think exist? Everything in engineering has trade-offs, okay, so will this. How many of you have ever run a virtual machine? Okay, how big are the files? How big is a VM disk image? Many gigabytes, right? So you'll have to move that over. Okay, now, so that would be the image. So if you do it naively, of course, this is going to be problematic, right? So you have to somehow make sure that you minimize that thing. So these guys obviously provide some solutions to that. You have a similar image there, and you kind of send over a delta, because your disk also has like your swap files and stuff like that. Kind of a lot of runtime state is there, so that needs to be kind of migrated over. So that's one issue. What about performance? Is virtualization going to cause a performance side? Absolutely. I mean, you basically are going through a level of indirection. So you could make the case that, I mean, I don't think they did this kind of analysis, but you could say, yes, I'm enabling sleep, but maybe I'm paying additional power consumption all the time now while I'm active. So that could be a problem. So these are issues there, but they certainly kind of simplify the process of going to sleep in terms of transferring the state. You do not have to deal with any special cases and all. It can work for any operating system, anything. You just kind of move over the virtual machine. So it provides undistracted desktop experience, OS agnostic, kind of all those sort of nice things. And essentially, now what happens is when they migrate the machine, you can still continue to access the machine, except that now you are going to access it through some sort of a remote desktop. Because your machine has a virtual presence which is always running, and that VM is just moving around. This sort of begins to also beg the question that why have powerful machine to begin with? Okay, so I don't know, any of you use Chromebooks or like, so Chromebooks is this machine that Google has been pushing very heavily, and the concept out there is that essentially I have a very lightweight terminal, and then my browser is a portal to cloud services, and everything else kind of runs in the cloud. So that's an extreme case of basically saying that, look, my machine has no state. All I have is a portal to my kind of personalized machine which is running on the cloud. Or another example would be if you use remote desktops. So CSNet runs these PCs as servers, and you can kind of access them, and you get kind of a customized thing. So that's the ultimate example of being able to sleep very easily, because when you shut your machine, there is no local state to preserve. You can just reconnect to that stuff. So these ideas are basically sort of going towards that. Centralized servers, I can do all the power management there. If I do not have any state on my edge machine, then shutting down the edge machine and making it up becomes a trivial problem. So that's what these guys are doing. Of course, the flip side is there are a lot of things that we like to do on our end machines which we cannot very easily in these kind of settings where the virtual machine is actually running in the cloud as opposed to running on your local machine. What would they be?
I can't play video games over the remote desktop.
That's just a speed issue. Let's say we took care of that. There are certain things which still remain intrinsically kind of difficult to do. Not speed wise, but sort of they're just plainly not supported.
I don't think you put in USB drives.
Right. Any sort of a local, like, I mean, we do all these embedded development and all, right? I mean, it's with Chromebooks and all, that's an issue, right? I mean, if you want to run a debugger or whatever, which is actively working through a USB peripheral or any other sort of locally connected peripheral. So certain kind of workloads, particularly the kind of stuff that we often end up doing and all, it's not going to work very cleanly. But for a lot of other stuff, I mean, you could see this being a solution. I mean, not for gaming, I agree, but let's say more typical non-IO intensive, non-compute intensive workload, that's probably fine. Okay. So anyway, that's they sort of showed some significant energy savings and stuff like that as usual. So this is how their system works basically. That very fast network, idle any desktop which is idle basically kind of its VM is just moved over to this big server where things are running, and you can imagine that. So I basically pushed the complexity of all power management out here. Here there may be multiple cores and stuff like that we can power manage them depending upon how many VMs we are running. This guy, all it has to do is to send out, release the VM to the other server or accept it back. So, issues that they had to face. Remember I said that VMs are huge, so you are migrating them. What is happening then? So what they do is they found a cute way of doing this to kind of hide the latency. So essentially what happens is as the virtual machine is migrating, so normally you are interacting with the virtual machine directly out here, but when the machine is, to hide this latency, they basically create this remote desktop client. Sure, you have always, like Microsoft offers a remote desktop client. There are also these VNC client servers. Okay, so that's the kind of concept. But the idea is that as this thing is migrating, you could basically begin to migrate this, and then at one fine moment change the connection of your remote desktop client from the copy here to the copy out here. So you can essentially hide away the latency. That's the trick that they end up doing. So they call it this concept of live migration. Okay, let's see. Other ideas in the literature. Another idea which people have kind of talked about is the following: peer-to-peer proxy. So essentially, kind of the concept is, I'm going home, my machine is going to go to sleep, but you are working late, so my machine state transitions over to your machine. Okay, so we essentially at all times use all the desktops in an enterprise as kind of a pool, and sort of essentially instead of a designated sleep proxy server, everyone is a sleep proxy server, and they can help out others. So what they typically do is any desktop machine is a candidate sleep proxy server, and then when a machine needs to go idle, or a laptop, or even a desktop, then we basically select out of that pool. So the nice thing out here is there's no additional proxy server needed, and also there's no single point of failure. You do not have a designated server. If one machine dies, maybe there are other candidates. There are issues out here. There are privacy concerns and things like that. Like, do you want data residing on a otherwise person A's machine actually being moved to a person B? And again, these are things probably with some encryption support and all can be taken care of, but one needs to provide that. Other comments, probably the sweet spot for home use. So at home settings, it's probably not, you'll not have like a proxy server and all. I mean, the load is just never there to kind of justify that. So the kind of solution where access point or your home gateway or whatever base station kind of takes care of it probably makes sense. In an enterprise setting, having a sleep server or maybe having sort of part of the network infrastructure kind of probably makes sense. Having simple proxying built into NICs, the network interface cards, is another kind of reasonable solution. Somnolink, which I had mentioned earlier, had a lot of splash, but eventually it didn't get much traction. And I think the reason basically is they made the design too complicated, because they tried to they provided all these capabilities of application stubs and all, and which is way too complicated. You suddenly have to ask Skype and whatnot to kind of create these applications where there are stubs which are going to be running on this other processor. I think now if you were to do it, the big dot little architectures are going to be the clean way of doing it. That's one possibility. The other possibility is that a very simple proxy where running on the NIC, which essentially wakes on everything. I can tell it, or I can give it some patterns. And so wake on Ethernet or wake on LAN was way too simplistic. It always woke up on any arbitrary packet. But instead, if I could tell my network interface that wake me up when a packet with certain matching criteria comes, otherwise keep me asleep. I think that would kind of that does the trick. So the idea then is the NIC is always powered up or powers up in case wireless frequently enough. And when it gets the traffic, it analyzes the traffic, maybe certain ports, maybe from certain IP addresses, maybe certain patterns being matched, like if it's coming from Skype IP address, wake me up. If it is carrying one of those particular TCP/IP port numbers, wake them up. So that kind of concept is another possibility. The issue with this is that NICs on old machines do not support these kind of patterns, and for complex networks there might be way too many patterns. So there is kind of a transition issue out here, which kind of never made this solution very attractive. So in principle, if you were starting from scratch, one could imagine kind of mandating that network interfaces should have this capability, and that would be kind of a nice solution. But now around these concepts, people have done a whole bunch of other kind of things also, particularly with the proxies in the network, like wake on swipe, wake on GPS coordinates. So kind of these kind of ideas that people are entering, they swipe their card in the building and their PC wakes up, or as they are within a certain geofence region, then the wake up happens. So essentially, a lot of other cooler services on top of it can be built, and this concept is there for a lot of other things also. Like for example, some thermostats now have this capability that when you are within a certain distance of your home, then the HVAC kind of comes up, as opposed to having it at a fixed time and all. So you can kind of always build up more sophisticated things if you have some sort of a network connectivity around it. Okay, so that's the connection of different schemes, how they kind of compare. Various dimensions. One is reaction policy, which is when is the sleeping node woken up? How much consolidation they do, that is it one-to-one or is it many sleeping machines get supported by a single hardware? How much change you require on the client? So like for example, the SleepServer or LiteGreen, they require a totally different type of client, whereas something like the Sleep Proxy or the Apple stuff, they basically are relatively minor changes. How dependent they are on the OSs, how much can they sleep, and of course the penetration that exists. So at this stage, I guess I would say it's technology which, at least in the current generation of hardware, is reasonably commonplace. Particularly if you are in a closed ecosystem where kind of the access points and all support it well. So that's where this technology kind of is. And again, well supported with some OSs, not so well supported on the other. So next up when it comes to power management is what happens on the network side of things. So we've kind of gone through processor, we kind of talked along the way a little bit about displays and stuff like that, but essentially the viewpoint thus far had been processor centric, and we looked at it at different scale. What kind of things you can do when you're looking at small pieces of electronics, and also kind of the previous slide set, we kind of looked at what you can do at the scale of the entire system. So next, and we touched upon a little bit on how networking kind of interacts with this. So next up really is the communication fabric itself, because it faces the same type of issues. That is, not everything in our network is needed all the time, active all the time. So very similar issues of shutdown and scaling and energy proportionality and all kind of come up. So a lot of people have been looking into essentially making the communication networks more power efficient. So I'm going to talk briefly about that. So when it comes to networks, there are two separate aspects that sort of come up. One is network itself uses energy. By that I mean the network is not something abstract. It consists of routers, switches, network interface cards, all of these things, and they themselves are energy consuming. And the second thing is that there is an indirect effect of networking, that is to maintain network connectivity and all your computers and all have to do some additional work, and we kind of saw that. So what I'm going to focus on is the first part, which is the direct energy used by network related pieces, so network interface card, your switches, routers and all, and what kind of considerations sort of go into that. So this was a very old slide in one of the very early lectures. The main point here is the following, that there's a fairly significant amount of energy footprint when we talk about IT energy is actually goes into the communication infrastructure. So this is just, and by communication here I'm including not just Ethernet and all, but kind of more broadly telecommunication infrastructure. So this is just somewhat old data out of old plot out of some data from Italy. So when we talk about communication, usually they divide communication infrastructure into a few different pieces corresponding to the core of the network and the edges. So very briefly, you can say stuff inside the home or inside your workplace. Access, so this would be like your cable modem or DSL. Metro transport, this is how they distribute it within an urban area. And the core would be kind of like a regional or national or international scale, kind of the backbone. As you might imagine, as we go up the stack, the power consumption of devices increases. So kind of our home networking and all devices are relatively low power, but by the time you're looking at stuff which is running on the core of the internet and all, these are huge machines. So just like we have data centers, we also have communication centers or network operation centers, which are just full of networking equipment. They're usually windowless buildings that you might just drive by and never notice. So like, for example, if you are going on Sepulveda up north, there is just before Moraga, where those gas stations and all, there is a Verizon building which comes up, which is their network operation center, so chock full of stuff. If you are on Ventura Boulevard in Sherman Oaks, there's a big AT&T building, again, just concrete monster, that's their network equipment center, where again, lots of routers and all, essentially all the wires from home and all kind of end up there, and dicto for Time Warner and all. So they're all around us, and essentially that's the link between home and access. And then, of course, it's the urban area stuff that's all over, and the core internet to stuff like that. So power goes up this way, but the flip side is number of devices grow up in the reverse direction. And so by the time you look at the overall energy footprint, actually from a societal perspective, there is a lot more energy consumption happening at the edges. But it's a harder one because we are talking about tiny little savings, but then they're being multiplied by millions and hundreds of millions of devices. So it's the right target out here, but it's a harder target. The easier target is out here, but then it's a less interesting target. Telecom consumes a fair bit of energy consumption, and this is data from US and all. Okay, so another thing I wanted to point out was some interesting kind of data. So when it comes to cellular networks and all, it turns out that energy consumption has become a significant issue there as well. Partly because of the type of energy, but partly because the infrastructure itself is very energy hungry. So, for example, each base station which is deployed consumes roughly to the order of a couple of kilowatts. So by the time you look at the whole year, kind of a total of significant energy consumption. A lot of it goes into RF because these signals, powerful signals, have to be transmitted over several miles. Then there are other associated costs. There is signal processing. There is also the HVAC or the cooling system. This essentially is equivalent to running a few small households. Okay, so that's the equivalent that each base station takes. Every year, hundreds of thousands of base stations are deployed. There are still sort of large parts of the planet where these are still being deployed, and also as we move towards LTE and kind of 5G, which is the new wireless, which is going to come in a short number of years, more and more energy hungry. Another issue which comes up is that oftentimes in remote regions, these things are operated using diesel generators and stuff like that, which again is kind of a dirtier form of energy. So what has happened is, from a network service provider perspective, also there is a lot of interest, because this is real money out of their pocket, because they have to run this infrastructure. Any saving there is basically savings in the dollars. And then it is further coupled by the fact that, as I mentioned earlier, that there's a lot of this notion of carbon credit, and also the governments are forcing companies to be more kind of efficient in this regard. So anyway, so upshot is that networks consume power, networks consume a fair bit of power, and it's, by the way, also one where service providers also care about, because this is money out of their pocket, and it's actually a fair chunk of their overall lifetime cost. So when you look from their perspective, they deploy a new technology, it's going to be there for a few years, that's the capital cost, but then the runtime cost is the energy consumption that they're paying for, so it matters for them. So, and of course, the other thing which kind of motivates this thing is that traffic keeps growing. Okay, so these are all trends that we kind of know of. Now, unlike computing, communications comes fundamentally limited by energy. Okay, what I mean by that is that the sheer concept of signal to noise ratio basically says that communication, that if I need to communicate with a certain degree of reliability over a certain distance, then there is a fundamental bound on how much energy that I do need to spend. And that's a good old sort of Shannon's communication theory, which kind of comes. So a big difference is computing. If you do it very slowly, you can consume asymptotically zero power. Communication, if I need to communicate over a certain distance with a certain accuracy at a certain rate, I have to pay for it in some form or other. Okay, so where does all of this kind of ends up with? So what kind of numbers are we see? So let's look at that. So at different layers of the network. So we use routers, we use switches, and things like that. Roughly speaking, the kind of numbers that we are looking at. So like for example, a router, 12 nanojoules per bit, or 12 milliwatt per megabit per second. A switch, 2 to 8 megawatt per megabit per second. So router is doing a more complicated job, so obviously more energy consumption that is happening. A lot of these trends are, I mean, if you look at the energy, some of it is the equivalent of RF energy, but a lot of it is electronics, and that keeps that is certainly improving. Let's look at our Ethernet. So I talked about different Ethernet standards, and that perhaps speed is something that we worry about. So let's look at LAN switch, different ports operating at different speeds. So 10 megabit LAN, 100 megabit LAN, 1000 megabit LAN. What you see out here is that there's clearly a huge baseline cost, because if you see, for example, at 8 ports, I go from 10 to 100 to 1000. There's not much of a power increase going from 10 to 100. That basically means electronics very similar. But when we go to 1000, we have some jump, but it's not a huge jump. Okay, so from going from a gig network to a 10 mega network, I'm still paying for a huge overhead, baseline overhead. So highly energy non-proportional in our setting. And the reason is that whether you are doing 10 or 1,000, there is also still a computer running, usually running an operating system, with a routing fabric, all of those things are up. What changes from going from 10 to 1,000 is kind of the signal processing part, which is doing the bit decoding and stuff like that. So not very energy proportional. This is another example. This is identical switches, 48 port layer 3 switch. So layer 3 switch is what you would call as a router. So essentially doing routing. And what you see is across different vendors, otherwise identical switches, significant variance. So like this switch is very inefficient. So that's one part. The other thing that you see is whether it's fully loaded or idle, not a whole lot of difference. So again, not very energy proportional. So current networking infrastructure, again, if you were to draw an analogy with what we started out with on the computing side, consumes a lot of energy and also is not very energy proportional. That is, even when we are not using it for anything, it still is burning a lot of power, and so that's not good. This is another look at the same kind of data. Yeah, more data. I'm going to ignore this part. Okay. So what has been happening on the networking side is that over the years, over the past 10, 20 years, we have had a steady rise. And if you look at your servers now, they often use 10 gig links. At any given point in time, when a new technology gets introduced, it's kind of early stages of technology, so some inefficiencies to be expected. But we are paying for this data rate in an increasing power. So at this stage, between 10 and 100, not much difference. Go to 1,000, we pay more. You go to 10,000, 10 gig, there is a huge increase in the power consumption. Let's see. Okay. Idle versus active power, relatively little difference. So again, goes to the point that not very energy efficient, and no correlation between performance and power. So all of this has led in recent years to kind of this focus that could we make the networking part more efficient? Okay, and there are a variety of different things that could do. One could talk about new types of devices. One could talk about new architectures, new protocols, and of course, new types of networks. So let's start with the similar observation that we had on computing side, that most energy in a lot of the energy in network is wasted. Networks are very lightly utilized and over provisioned. So just like we had those plots of servers which are mostly idle, same thing if you were to look at traffic on your network, they are mostly idle, but nevertheless we have very high peak rates. So why do you think we go for very high speed networks when they are so grossly underutilized? Let's work differently, okay? You probably use, I don't know, let's say 3 or 4 gigabit per second of data out of your mobile phone over the course of a month, if at all, if even that. You divide it and you're looking at a very fraction of the speed of the LTE, right? I mean, but of course we all still want LTE, and same thing with the home and all, right? Or our machines, I mean, while in an aggregate sense, your 10 megabit Ethernet is probably sufficient, but we still like to have the higher speed one, okay? So why do we over provision?
Occasionally we want
the higher speed, right? So it's the latency that also matters occasionally. So we do want that higher performance, but then the flip side is we somehow need to make things more energy proportional so that when we are not needing it, we kind of scale down nicely, okay? So now network elements, as we kind of, those numbers sort of showed, they have a very high base power. That is, whether we were transmitting at very low speed or even idle versus whether we're transmitting at high speed, kind of a big part was, you can think of this base power as kind of like my leakage power, which is the mere act of having that equipment and keeping it up basically consumes that power. So what all of this suggests is that just like on the computing side, on the networking side also, if I can find clever ways of shutting the equipment down, I have big gains to be had. So the goal again is energy proportionality. We want to operate in a setting where I'm very efficient even all across the spectrum of utilization. So what that has led to, if you have bought a switch in recent years, you would see these labels like green Ethernet or some 802 dot some code associated with it also. So what that has led in recent years is to create variants of Ethernet, and likewise on the wireless side, where I could do shutdown very efficiently. So this is the same slide that sort of I had earlier on, which is if I look at network interface card, and if I look at its power consumption, so this is the Ethernet chip and the PHY chip, which sits in front of the Ethernet and drives the signal on the cable, and both on the computer side and the analogous stuff on the port side, what you would, so what you see out here is gigabit per second link with no data, 100 megabit link and a 10 megabit link. And as you would imagine, and this is kind of the power consumption which is happening as the number of links are going up. Yes, you pay for higher performance quite dramatically. As the number of links go up, the performance. But now if you monitor what is happening on your link, so this is a desktop computer running on a 100 megabit Ethernet. This is how the traffic looks like. Okay. Mostly nothing is happening. Once in a while packets go out, most of the time not much is happening. So somehow, so the utilization in this particular case is 1%, insanely low. So if we were to look at it purely from utilization perspective, we are basically looking at a megabit per second link. But for reasons of performance like voice telephony, video gaming, those sort of things, we do need a faster link. This is a gigabit link to a server, file server over a 30-minute period. Again, what you would see is, yes, there are bursts. In fact, some bursts are going all the way to like 80-90%, but most of the time nothing is happening. So again, utilization is very low. So the question then is there a way we could make our communication links go up and down very rapidly so that we can exploit these idle times? Because otherwise, essentially what is happening is, relative to what we need, we are paying some 100x more energy if the utilization is 1%. So there's a lot of headroom. Could we somehow make use of that? So links are lightly utilized, and they are likely going to stay that way because that's just the nature of our systems. When link utilization is low, we do not need the high bandwidth. So could we slack things off? So instead of, so how do your computers, like, let's say, so I'm not talking about wireless, but let's say you buy a desktop and you plug it to the network. How does it know what speed to run at? Like what Ethernet speed it takes? Huh? No. Actually, so the question, does the speed change packet to packet on Ethernet?
Does the speed change when?
When is the speed decided, I guess that's the question. Like, have you ever bought a computer, plugged it to Ethernet, and wondered about like what speed it's operating at? Do you have to do anything, set up the speed?
It appears to be automatic.
Okay, so it appears to be automatic nowadays. But what happens then? I mean, there are clearly two parties involved, right? There's a switch, there is your computer. Obviously, if you buy a fancy computer with 10 gig Ethernet, but if you plug it to our CSNet network out here, it's not that it will operate at 10 gig, right? I mean, there's the other party also, right? So both have to have kind of the same thing. So old days, it used to be that you had to tell the device driver of the Ethernet card that you operate at 10 or 100 or whatever setting you're doing. Nowadays, it is automatic, but it decided once at the plug time. So how many of you have routers at home or switches at home? I mean, most of you do, right? The Ethernet jack usually has LEDs and it tells you whether it's operating at 10 or 100. And it's decided at the plug-in time. Okay, so what happens is when you plug in the device, at that time it goes through a negotiation, and then it sets the speed, and then that's what the speed remains. Okay, so the goal there is they try to set it up so that you're operating at the highest speed. So if my computer is capable of 100 and the switch is capable of 10, they will select 10. If both are capable of 100, they'll select 100, and then it stays that way. And if they decided it both can support a gig, then it will select gig, and then it remains constant in that. So there's no shutdown and there's no scaling, and the goal is always maximize performance. And the convenience factor in recent years has been that you do not need to set it up. They kind of do some negotiation, and then they discover what the highest speed both sides can sustain, and they set it at that. So, but at the same time, those numbers we saw, particularly as we go from 100 to 1,000 or 1,000 to 10,000, there's a steep increase in the power consumption. So the current standards have been optimized for speed and convenience, and not for saving power. So essentially, the speed is fixed or negotiated at the beginning, but then from that point on, circuitry always runs at that high speed. Interesting data points, like all the network interfaces consume terawatt hours of energy, essentially huge carbon footprint and stuff like that. So if we could save there, if we could enable network interface cards to shut down or change their speed dynamically, then there is some interesting gains to be had out there. And particularly once you start looking at higher speed mix. So what has happened on the standard side in recent years is that they've tried to address both these issues. Scale the rate with the load. So having Ethernet where the rate changes with the demand, and then shut down when idle. Now interestingly, these two things are also faced in wireless, but since wireless was always designed with batteries in mind, battery life in mind, so these things were always part of the conscious decision making. When it came to Ethernet, energy was not considered to be an aspect, so it's been more of a recent addition to kind of creating green Ethernet and all. But now you can indeed, like if you just look for like an Ethernet switch for home and all, you would see many of them advertise themselves as supporting the green Ethernet standard, and which kind of came into being in recent years only. So early work in this space was adapting rate to the load. So kind of the idea is that you monitor the traffic going over the link, and if the data rate is high, then I'm going to change the actual link rate, the physical layer rate to increase. And so that leads to the questions of what is the mechanism and what is the policy, okay? And then how long does it take to kind of do this switchover and stuff like that? And could it be that my network will keep oscillating? Is the complexity justified and all? So an initial idea in this case was that could I somehow make use of the auto negotiation that already exists in the Ethernet? So I was talking about when first time you plug in your laptop, like when you hook up the cable, it immediately goes through this negotiation process. And that's how it decides what is the highest speed which is sustainable. So originally this was sort of optional, but then it pretty much became standard because they didn't want people to be messing with the device driver setting and all. And then once the 1 gig Ethernet came into being, then it became mandatory. So kind of idea is that two devices, essentially when they're connected, they decide on a bunch of things. They decide on speed, they decide on whether it is full duplex or not, and whether what kind of flow control is there. So another thing you may have noticed in recent years is the following. It used to be that Ethernet cables used to come in two varieties, crossover cables and direct cables. Okay, crossover cables had receive and transmit swapped. And the idea was that if you're connecting your laptop to a switch versus a laptop to another laptop, you would need different kind of cables. If you connected a computer to a computer, you needed a crossover cable. If you connected a computer to a switch, you would need a regular cable. And the reason was because in the jacks receive and transmit are on particular pins, so you need to swap them because these jacks came in kind of two varieties. Again, used to be a big pain. Nowadays, you would see say this is auto negotiating. So again, what it does is when you connect it, it negotiates and figures out, adapts to that. So there's already, starting from 1 gig Ethernet, there's already this process in place. It basically says that the Ethernet chips have to be smart enough to negotiate what is the highest speed sustainable, whether there is duplexing or not, and some other parameters out there. So it negotiates the best possible thing, but its purpose was primarily at the startup time. You connect it up, at that time it happens. So what happens in this particular case is the following, that at the physical layer, there's a set of pulses which kind of go back and forth, and right after connection, and during that time these things kind of get negotiated. Okay? The problem is it's too slow. So you could conceivably imagine an approach where I could use this approach to change the rate on the fly. I could essentially conceptually disconnect or whatever, use this negotiation process to negotiate a new rate right at the physical layer level. But the problem basically was it was never designed for this kind of a rapid adaptation kind of thing. So essentially what happens is a bunch of these pulses go out, like I said, these pulses carry information about what the speed of the link is, whether it can support full duplexing and all. So this, again, this capability always there, but would not work easily. So you could say this is the counterpart of like an existing technology which could have been used but was not very efficient. So what that led to is this notion of adaptive link rate. So idea is that could we more rapidly adapt the link rate of the Ethernet during peaks of as the load changes. And no physical layer changes should be kind of required. So that is kind of a standard emerged. And in this particular case, what happens is that your machine talks to the LAN switch. Both of them have to support this capability, where essentially a particular MAC frame goes out, which has a rate adaptation request, and then resynchronization to the new rate happens, and all of this takes kind of a few milliseconds, as opposed to doing it this particular way, which would have required seconds of switchover. So switches, so that was this ALR mechanism came into being, or was one of the proposals. I'll talk about how it didn't make it. But otherwise, the basic idea is on either side, you kind of monitor the packet queue. If the packet queue exceeds a certain threshold, on the high side, you increase the rate. If the queue becomes too low, you reduce the rate. So both sides monitor the queue, and depending upon how occupied the queue is, they kind of change things up there. The standard which eventually emerged was and sort of came in 2010 is the energy efficient Ethernet, and that did not use this ALR approach, but rather it ended up using something called LPI. And the basic idea behind the LPI, sort of the way these things work is when early on, sort of the interest emerged in this in 2005, they form a study group. Every company kind of puts their proposals forward, a lot of negotiations take place, and eventually the standard emerges, and then after that, products begin to come into play. So, 5-6 year process in which they evaluated different things. So, early work on ALR, then became some other proposal, and finally kind of became what is called as LPI, and I'm going to describe that briefly. The issue was that ALR was this handshake-based speed change protocol, and what most vendors felt was that it was too complicated. That is, a lot of messaging and all that was needed. And the other issue which came up was that the switching time was perceived to be complex enough. Every time you change the speed, the physical layer has to retrain. So what happens at the physical layer is, as we are going to higher and higher speed, what physical layers have to do is they have to learn the channel characteristics. So they send some training packets, they learn the channel characteristics, they adapt the filters on either side, and then they operate on that. So every time you change the speed, all of that has to be redone, and that was felt not to be a worthwhile endeavor. So for the actual standard, they set out certain sort of goals which kind of took this into account. Eventually, what they ended up was this notion. LPI stands for low power idle. So basically, the idea is during the idle mode, could I switch to essentially the equivalent of shutdown. So upshot of all of this is instead of scaling the speed and all, it basically decided when it is idle, could I switch to a very low power mode where I can idle in a very power efficient fashion. So skip over. So the key principle out here is the following, that if I look at the link, there would be times at which I am up, and there are times at which so there is activity, and there are times at which there is no activity happening. So whenever there is no data to be sent, you basically enter into this idle mode. So this is a shutdown equivalent. But we keep transmitting a wake up signal during this idle time so that you can rapidly wake up. So in a nutshell, scaling didn't work out because in a processor, scaling is easy. You change the clock, it runs at a different speed. In a communication setting, scaling is hard because every time you scale, you have to relearn the channel characteristics, and therefore the delays involved are too rapid. Delays involved are too complicated. So what won out on the communication side for Ethernet is this just simple shutdown, and coupled with some periodic refreshment messages. So at some stage you decide to go to sleep, and you sleep, but you keep a heartbeat going so that you can rapidly wake up. So these are some kind of numbers, the amount of time it takes to sleep, and so on and so forth. But point is, this is a much more agile, much speedier scheme. So this is what exists. I want to skip over this, but basic idea is that if you have a switch, and most computers now support Green Ethernet, they basically go to sleep whenever the link is idle. They keep sending a heartbeat, and then they wake up. What is helped by is also the fact that with Ethernet, we have a direct point-to-point connection. So every port on the switch is connected to one device. So you can individually kind of make things go to sleep. Okay, so we'll skip these. Another optimization that I think they do now for Ethernet is to combine packets. So bundle up a lot of packets into a single large packet so that you can also optimize the idle time. So that's called packet coalescing. So to summarize, on the Ethernet side, what has then happened is scaling didn't work, even though that seemed very promising. What now exists is this simple scheme. You're idle, some sort of idle time policy. You bring both sides of the link to a low power state, but you keep sending this refresh message, and then when you want to bring it up, you rapidly bring it up. The rate adaptation schemes then sort of So now let's look at wireless side. So wireless standards started dealing with issue of power very early on because just because of this setting. So this is a slide I had shown earlier when we were talking about radio models. So we have electronics, we have RF on the transmit side, and then we have electronics on the receive side. And I had also talked about that how over long range rings, this will dominate the RF, whereas for short range rings, the electronics dominate. And it's very easy to also enter into situations where your receive is more expensive than transmit. And we also saw the backscatter radio, where again kind of some of these things change, like transmitter does not have to provide its RF. RF is actually on the receive side. What all of this translates into is the following. If I look at my trade-off between between various kind of energies, so let's say I have to send certain amount of data, and I tell you that I have a certain deadline. So you have two strategies, much like the processor. I can transmit very rapidly at high speed and then shut down, or I can transmit slowly and occupy all the time. Now, as I change that time duration over which I'm transmitting, these different energies or different powers, namely the RF, electronics, change differently. As I take more time to transmit, I'm going to burn more electronic power. So that energy consumption is going to go up. So you can think of this thing as a little bit like leakage. RF power behaves differently. So this goes back to the way Shannon's capacity theorem works. If I have more time to transmit, I can transmit with lower power and lower energy. So each bit is going to take lower and lower energy. So the curve looks something like this, a convex curve. So I have more time to transmit. I can transmit the same bit with lower energy, all things same distance, same accuracy, same error probability, but with a lower energy. So you combine the two together, your total transmit energy looks something like this U-shaped curve. That is, if I have to transmit very rapidly, I'm going to be dominated by the RF energy consumption because I have to pump out a lot of power to sustain that rate. If on the other hand, I'm transmitting very slowly, then my RF component goes down, but my electronics is going to be up for a longer period of time, so it is going to look, going to begin to rise up. So question for you, which realm, which regime distance-wise do you think am I, so if I'm on short range, where in this curve would I be? So I have a short range radio, a Bluetooth radio, things like that. What would be the dominating factor? Is it electronics or is it RF? Electronics, and therefore I'm going to be somewhere around this. Another way of saying is that for short range radios, this the minimum point of the curve is going to be way to the left because I'm basically almost always dominated by the electronics. If on the other hand, I'm looking at long distance transmission, a cellular or a long Wi-Fi link, then I'm going to be almost always RF dominated. And therefore, that's another way of saying that this bottom of the curve is going to be way to the right. Which one of these would scaling help? So by scaling, I mean just like we did voltage frequency scaling, or in case of Ethernet, adaptive link rate. That is, I lower the link rate to occupy all the time. Is that a good strategy for short range, namely electronic dominated type stuff, or is it a better strategy for long range, namely RF dominated stuff? So imagine I give you a deadline, you have two strategies. You can scale the rate to occupy all the time, or you can transmit ASAP and shut things down. What kind of radios would, for long range versus short range, where would the strategy of scaling, that is slowing things down and occupying all the time, would work? better for the long range one, and why is that? Well, I'm basically on the falling side. This curve, this is way to the right? So as I slow things down, I'm always just benefiting. If on the other hand I have a short range radio, then most of the curve would look like this. This bottom would be way to the left. So therefore, if I spend more time, I'm actually taking more energy. So, or another way of saying is like plots look something like the following. For a short range radio, the curve would look something like this. The bottom would be way to the left. If I have a long range radio, the bottom may not even exist or be way to the right. And therefore, strategy-wise, scaling is better if I have a long range radio. Shutdown is better if I have a short range radio. Okay, there's not much benefit to be had by messing with adaptive rate and all, whereas with cellular radios, that's long range Wi-Fi, Wi-Fi type stuff. So Wi-Fi is somewhere in the sweet middle spot where you'll probably have a bit of both. But for things like Bluetooth and all, it's or Zigbee or these kind of radios, it's very important to be able to rapidly shut down and wake up and have very low power consumption otherwise. Okay, whereas for cellular radios and all, it's very important to be able to scale. So what that leads to is much like so in case of Ethernet also we see similar effects. Okay, so actually I should say another point also. While I have specified things here only in terms of range, very similar things also hold for rate also. So if I have a higher rate radio, then again I would have to send many bits in a single symbol that I'm sending over the air, and therefore I'm going to spend a lot of power. Okay, and so again the curve would look more like the long range curve, that is, scaling is going to help at very high rate radios. So in case of Ethernet, we saw that while there was room for scaling, because 1010 gig Ethernets were very power hungry, but the way the standards worked out and all, scaling never happened. In case of wireless, scaling does take place. In fact, your Wi-Fi radios all the time scale the rate. Some of it is because of maintaining link robustness, but some of it is also to minimize power consumption. So for radios, there are two broad schemes then. There is shutdown, and essentially much like processor shutdown, the idea is that I have some deadline by which I could transmit, but I'm going to transmit instead of occupying the entire time at a lower rate, I'm going to transmit as quickly as possible and get rid of it. So same kind of questions we had on processor come up: when and how to wake up, when and how to go to sleep. One way to deal with this thing is to have specialized protocols to arrange for this wake up, and another is to have some secondary radio, often called as wake up radio or paging radio, which arrange for the wake up. And the second scheme is scaling based stuff. So kind of the idea is that if I can find some way to operate my radio at anywhere along this link, which is I can dial the speed down and improve things. So dial the speed down and reduce power consumption, or dial the speed up and increase power consumption. Question then becomes, what is that knob? So in case of processor, we had voltage and frequency. In case of radio, remember, particularly here, we are talking about mostly RF power. So voltage is a non-issue. You pump up the voltage, that's not going to do anything. So you need to find some other knob. And that other knob usually comes from, in literature at least, a couple of things people have explored. One is modulation scaling. And kind of the idea is I can transmit things faster by sending more bits in a single physical layer symbol. So instead of using a binary code, I can use, let's say, instead of sending 1 bit, I can send 2 bits or 4 bits or whatever, more bits into a single symbol. So essentially, same baud rate, but higher bit rate. As I do that, I basically transition this as I increase the number of bits, the transmission time will go down, but I will pay a lot in energy. So this is equivalent to our voltage curve. Another one is coding. Coding for error correction. So I can code more heavily. When I code something, I have to send additional bits, but I increase the robustness of the link. So effectively, I can get more bits across. It's equivalent to essentially spending more power for more capacity. So code scaling and modulation scaling are the two schemes which are used. So idea is that I will set my modulation or coding so that I make use of the entire transmission time. So I'll transmit as slowly as possible. I will benefit from a reduced RF power consumption, but I will pay for increased electronic power consumption, but I'm going to come out ahead because these gains dominate. So radios use both these mechanisms depending upon what range they are optimized for. There is scaling, there is shutdown. If it's a short range radio, the sweet spot is going to be way to the left, and essentially your strategy is going to be one of shutdown. If it's a long range radio, the spot is going to be the right, and essentially your strategy is going to be one of scaling. So Wi-Fi, cellular, you'll find scaling. Bluetooth and these kind of radios, they are dominated by shutdown. These radios are designed for very rapid wake up, very quick stabilization of clocks, things like that, so that you can quickly shut them down, bring them up, small headers, things like that, everything that you would expect for making shutdown more efficient. Whereas when you look at cellular radios and all, everything that is needed for making scaling more efficient. And then Wi-Fi falls somewhere in the sweet spot. You would see both kind of mechanisms there: shutdown, scaling. So while you're active, scaling takes place, but then there is also, like we saw, wake on wireless and all those kind of things where shutdown happens. So at this stage, these are in all the standards that exist, Wi-Fi, Bluetooth, and all. There are various kind of power management stuff built in for these capabilities. So this is an example of how, for example, the equivalent of dynamic voltage frequency scaling gets done for radios or network interfaces. The idea is a radio, there is a queue. Somehow I can change its modulation scheme, and again, Wi-Fi radios and all provide this capability. What the processor does is it monitors this queue. If the queue starts getting filled, you increase the rate. If the queue is relatively empty, you can reduce the rate. And because of modulation scaling, you have sort of significant benefits to be had. So lots of work along this direction of energy-aware packet scheduling, things like that. But these are at this stage kind of common part of the standards around us. I mentioned that coding is another knob which exists, and it works very much the same way, which is if I have more time, if I have less time versus more time, I can change the degree to which I'm coding, and I essentially have another. So you can think of code and modulation as like our voltage knobs. So all of these things come together in wireless devices, where the CPU, the sensors, the radios, and all of these things kind of come together and they coordinate. So some people have looked into how, for example, I can change voltage. I can change the voltage of the CPU and the frequency of the CPU together with the modulation scaling, modulation and coding of the radio, and kind of essentially coordinate all these different knobs. So your CPU is giving you a speed performance knob as well as ability to shut down. Your radio is giving you a speed and performance knob as well as the ability to shut down, and you are coordinating all of these things through some sort of intelligence sitting in the operating system and the protocol stack. There is a complication, and which I'm going to touch upon next time, is the following. In case of CPU, wake-up events are local. That is, if I have to wake something up, there's a keyboard, there's an interrupt or something like that which will wake things up, and things are easier done. The radio, the problem we face is that there's a radio which is sleeping, and I need to wake up by sending it a message, but the radio is sleeping. So the solutions to those, I kind of briefly alluded to thus far. One is that the sleeping radio can periodically wake up and say, aha, are you trying to wake me up? And kind of listen for that. Or the alternative is I can have a very low power secondary radio, which is always up, and I can use that to wake up. And that's the concept of the paging radio or the wake up radio. So those things are kind of around as well. Let's talk about sensors. So that's a piece I have not covered. Do you think these ideas of scaling, so shutdown always works. Do you think scaling works for sensors also? Or what kind of sensors might it work? Okay, so sampling rate is one, but would you change sampling rate? So let's talk about what might be my scaling knob in a sensor. So let's say I have speech, microphone, I'm sampling the microphone. If I change the sampling rate, what changes?
Depends on the variation of the data. So if there is a lot of variation, you need a higher sampling rate.
Right. So it's called Nyquist sampling, right? So essentially, if I am sampling a signal, let's say it's an ECG signal or a speech signal or something like that, if I am changing the sampling rate, then my A to D converter is going to operate at a lower rate. I'm certainly going to win. But what am I losing? I'm losing in the information content. I cannot capture information in certain frequencies now, right? So if you think of my spectrum, if I'm going to be sampling at rate X, I can, my bandwidth I'm going to cover is X over 2, and therefore I'm going to be missing out any information above that. I also obviously have to filter. There are newer sampling techniques. How many of you attended this talk on biosensors, which professor from EPFL gave like recently in the department? Anyway, he talked about this, like they were using this thing called compressive sampling, which is a way that you can sort of capture more information than what Nyquist rate will imply, but kind of ultimately the principle holds. If I'm going to sample at a smaller rate, then I'm going to miss out on some information. Yes, but most signals, most real-world signals express sparsity in some domain. Okay, so that's one. Okay, I can change the rate at which I'm sampling. What else can I change?
The data sends out.
Hmm?
The data send out.
What do you mean data sent out?
Like how you can compact data, or do you choose like to do local processing instead of send out everything?
Okay, so I can compress data and stuff like that. Okay, sure. So I could capture the sensor data and compress it before sending it out. I would put it more into the category of games we are playing on communication side as opposed to actual sensing. So when it comes to the sensor, again, what are the knobs where I can dial the knob and I can change the quality of sensing? I guess I could take a variant of yours which is I collect all the data and throw some of the data. Okay, so I could do that. But do you see some other intrinsic knob that sensors offer which I can use to, Resolution, okay, so I can change number of bits, right? I have an image, 8 bit per pixel versus 10 bit per pixel versus 1 bit per pixel. We saw it on the display side, color versus black and white, you can imagine, or with microphone. Okay, so the second knob we have is essentially adding quantization noise, right? I mean, you basically change. That's the second one. What else?
Can you give another example of sensor?
I don't know, temperature, ECG, accelerometer, gyroscope. There are all these examples, right?
For example, if AC is sensor or something like that,
Hmm?
the sensitivity for the received signal, some sensors cannot work with low power signals and with high power signals.
Mm-hmm.
I mean, the sensitivity of the system.
Yeah, sensitivity. So basically, I can, what is the range of signals I'm willing to capture? So essentially, how sensitive am I? Can I capture very low range signals, or can I sort of can I afford to miss them out? So I can dial the sensitivity, which in effect affects the amplification stage, and I could therefore use that. Okay, I can dial the sensitivity of the sensor. To say another example, another way of looking at it is take an image sensor, cameras, right? So you have multiple parameters out there, right? I mean, you can change the pixel size, you can change obviously the resolution and all, but we also, by changing the amplification, we affect the ISO speed of our cameras, and therefore when we can operate it in dark, but at the cost of more noise. So I can always play games with the analog capture stage, again, save power and all of this. So sensors offer a lot of these scaling opportunities also, okay, and again, kind of the issue is probably going to be, I could also play games on the processing side, like for example, the type of filter you apply or how much work you put into processing that image or processing that sensor data. And finally, actuators are also going to offer similar capabilities, namely performance versus power, kind of a trade-off. And of course, you can always shut down. So shutdown is always an option, but scaling is also kind of an option. And I think scaling tends to be more complicated, but it's more, it gives a natural feel of energy proportionality. Shutdown is easier to manage, and sometimes that reduced complexity is the one that kind of drives things out. So let's see. Yeah, so I guess I'll see if in one of future lectures I cover a little bit more about the sensors we think, but radios and CPUs are kind of the one which are most well studied. So I'm going to stop at this stage.